Hey guys, welcome back. This lecture is on complexity analysis. It's very crucial to know about how to analyze the complexity of any algorithm. And here, the complexity is concerned about how fast or slow a particular algorithm or a piece of code performs. So in previous lecture, we were discussing that a problem may have more than one solutions. Question is, are they all equally good and efficient as each other? Answer is no. So what makes a solution better than others? Well, obviously, it's the efficiency or the performance of the algorithm. And we judge performance of any algorithm with complexity analysis. There are two kinds of complexities that we do care about: time complexity and space complexity. Time complexity, where we check how fast the algorithm runs, and the space complexity is about how much space or memory the algorithm uses up. We will discuss these in detail later. For now, just remember, algorithm having better complexity is a better solution. Though some algorithm may have better time complexity but are not good in case of space complexity, or vice versa. It just depends on the problem or the situation that how you want your code to work. Now let's see, how do we calculate complexity. In case of time complexity, we check how fast our algorithm can execute. But how can we express it? In seconds? In milliseconds? Well, if you try to compare them with time, you may find a single algorithm taking slightly different time at every execution, as there may be a lot of stuff going on in our system that may affect the execution time. Because there can be multiple factors affecting the execution time. For example, the execution time depends on how fast the code or algorithm fetches data from cache or main memory while getting processed. It depends on how many processes or tasks are running at the same time, etc. Other than these system-specific dependencies, the runtime for any algorithm also depends on the fact that how much data it is going to process, that is on the size of input data. For instance, think of a case: you have an array of size 10 and your function returns the sum of its elements. Maybe for that it's gonna take few nanoseconds or something. It will be quick even for 100 or 1000 elements, but it won't be that quick in case of 10,000 or a million or a billion elements. So the most important factor that affects the execution time is input size. And here we got that time complexity is not just about how fast your algorithm is, it actually cares about how fast the algorithm runs when the size of input increases. Now if you go ahead and start measuring it with some time unit like seconds or milliseconds, then it would be senseless. It is senseless to say that for this particular size of input, the algorithm is taking 5 seconds, 5 milliseconds, 10 milliseconds, or a second. We cannot say that. So to actually define it, there is more reasonable way. We won't measure time complexity in seconds. Instead of doing that, we will measure the change of speed of the function as the input size increase. And here in this function, sum, it's going through every element. So increasing the size of input array will affect the execution time linearly. So the complexity here we represent by writing ON. We symbolize the complexity using notations, and this O here stands for big O notation. If we draw it in a graph, where at x-axis we are having number of inputs and at y it's the number of operations, then the result will be like this. So it shows the linear relationship between the both. For n number of inputs, system has to perform n elementary operations. So the unit we use to analyze the complexity is the number of elementary operations in case of time complexity and number of memory slots that our algorithm is going to use in case of space complexity. Now let me sum up things that we discussed till now and let me clear this more to you. In order to analyze complexity of any algorithm, we actually analyze the behavior of function as input of the function increases and tends toward a value like infinity. And that's called asymptotic analysis, where in analyzing space-time complexity, we actually care about the growth of time or space taken by the algorithm with respect to the input we pass to it. We'll mostly discuss about time complexity throughout the course, but the space complexity is equally important and is calculated in same way. Now in computer science, we mostly use big O notation to represent the complexity because it calculates the complexity in worst case scenario. That is, we analyze function's behavior in worst case. Like what's the worst complexity this algorithm may have. So we think of the worst situation that is possible for that algorithm. For example, in an array, you need to search a particular element. For that, you need to traverse through the array. You need to check each element. Here, the best case is that we may find the element at the very beginning of the array. And average case is when we find it somewhere like in the middle. And the worst case is where we find the element at the end. So we calculate complexity for the worst case. Other than that, there are notations like theta, omega, and many more that are used to define complexity but are not accurate and useful. So we use big O notations. So by now, I hope you have better idea of what complexity analysis is about and what unit and notations we use to measure the complexities of any algorithm. So that's all about this lecture. Let's move forward and see how we can calculate complexities for algorithm and what are the basic and most used complexity values in detail. So guys, see you there in the next lecture.